Hey class, we are going to look at revisions on reaction kinetics. For reaction kinetics, there are three subtopics. So 1.1 on reaction rate, 1.2 on collision theory, and 1.3 on factors affecting reaction rate. So we shall look at 1.1 reaction rate first. So for PSPM revisions, we are going to focus on the learning outcome of C3 and C4. And for 1.1 reaction rate, the first C3 learning outcome is 1.1c, determine reaction rate based on differential rate equations of a reaction. And here is the example question related to differential rate equation. So in exam, how are we going to know whether the question is related to differential rate equation? So we shall see rate of formations of something or rate of disappearance of something in the question. So when we see rate of formations or rate of disappearance of a substance in the question, then we must know that the question must be related to differential rate equation. So to solve the question related to differential rate equation, so step number 1, we must write the differential rate equation based on the balanced chemical equations that is being given. So to write the differential rate equation, we must start with rate equal to, so N2O5 is the reactant. We know that in a reaction, reactant will continuously being used out. Therefore, when we write the expression, we must include the negative sign indicating that it is a reactant and the concentrations will continuously decrease as the reactions proceed. And then we must know that what is reaction rate? It is referring to change of concentration of reactant with time. And based on the balanced chemical equation, the mole is 2. So when we write in the differential rate equation, the mole, the coefficient, we write it as 1/2 equal to, so NO2 and oxygen, they are product. As the reactions proceed, product will be formed. Therefore, when we write in the differential rate equation expression, product will have the sign positive, means that it is being formed throughout the reaction, and the concentrations of product will increase as the reaction proceeds. And in the balanced chemical equation, there are 4 mole of NO2 being produced. So to write it in the differential rate equation, we must write it as 1/4. And for oxygen, again, it is the product. So therefore, it will be formed as the reactions proceed. Therefore, when we write the expression, we must have the positive sign in front. So change in concentrations of oxygen with time. And for oxygen, 1 mole of it being produced. Therefore, in the differential rate equation, we write it as 1/1. So this is step number 1. We write out the differential rate equation expression based on the balanced chemical equation. So step number 2, we must look at the question, what is being given and what we want to find. So we are being given the rate of disappearance of N2O5, which is equal to 1.25 times 10 to the power of -2 molar per minute. So N2O5 is the reactant, and therefore it will disappear as the reactions proceed. Okay, so therefore to write the expression, we must have the negative sign to indicate that it is a reactant and the concentrations of it will decrease as the reactions proceed. So negative change in concentrations of N2O5 with time is equal to 1.25 times 10 to the power of negative 2 molar per minute. And in the question, we want to find the rate of formations of O2. Rate of formation indicating that oxygen is the product, and therefore it will continuously be produced as the reactions proceed. So we must have the positive sign to tell people that oxygen is the product and it will continuously be produced in the reaction. Therefore, the rate of formation of oxygen is written as the change in concentrations of reactant with time. And we want to find what is the rate of formations of oxygen. Then in step number 3, we can solve this based on the relationship given for N2O5 and oxygen in the balanced chemical equation. So we know that for N2O5, based on the balanced chemical equation, it is corresponding to 2 mole being used out. So 2 mole. And for oxygen, it is equivalent to 1 mole being produced in the reaction. Then to solve it, we can do cross multiplying. We know that rate of disappearance of N2O5 multiplied by 1 is equal to the rate of formations of oxygen multiplied by 2. And the rate of disappearance of N2O5 is given this much. So we can just substitute in 1.25 times 10 to the power of negative 2 molar per minute multiplied by 1 equals to rate of formations of oxygen, we want to find, multiplied by 2. Therefore, to find the rate of formations of oxygen, it is equal to 1.25 times 10 to the power of negative 2 molar per minute divided by 2. We just bring the 2 over, so it becomes divide. Okay, and that should give us the answer equal to 6.25 times 10 to the power of negative 3 molar per minute. We don't leave our answer in this form. We must rewrite our answer as, therefore, the rate of formation of oxygen is equal to 6.25 times 10 to the power of negative 3 molar per minute. The next learning outcome that we are going to look at is 1.1g, asks you to determine the order of reaction involving single reactant using initial rate method, half-life method, and also linear graph method. We shall look at initial rate method first. In exam, how are you going to know that the question is related to initial rate method? So if the question is related to initial rate method, usually you are being given data for a few set of experiment. Like for example, in this question, you are being given 4 set of experimental data for 2 reactants. Then you must know that you must solve this question using initial rate method. So sometimes the question not asking the order of reaction, but then asking you to write the rate law of the reaction. You must also know that you need to use initial rate method if you are being given a few set of experimental data, because you can only write the rate law or rate equation based on the order that you determine for each of the reactant using the experimental data given. So for initial rate method, how do we find the order of reaction for each of the reactant? So first, we must write the rate law, general rate law equation first. So like for example, in this question, we have two reactant, CH3COO, CH3 and OH minus. So we must write the general rate law or rate equation for these two reactants first. So the general rate law or rate equation should be written as rate equals to K, the rate constant, multiply with the concentrations of CH3COO, CH3, and the order of the reaction is unknown, so we can write it as X first. And another reactant is hydroxide ion. What is the order of the reactions? We don't know. We can write it as Y first. So if the reactant given is X and Y, then the order you shouldn't write it as X and Y. You can use other alphabet to represent the order. Okay, like for example, you can write M or N. Okay, so but for this question, since the reactant is not X and Y, so I use X and Y to represent the order of the reaction for CH3COO, CH3 and OH minus species. So after you have written the general rate law or rate equation, then you can determine the order with respect to each of the species. Like for example, if you want to find X, the order with respect to CH3COO, CH3, then you must make sure the concentration of another species, so here is the OH minus, remains constant. Then you need to look for the experimental data where the concentrations of the OH minus are constant. So in this question, can you see that the experiment 2 and experiment 3 data having the concentrations of OH minus concentration remain constant. So means that to find our X, we need to use the experiment 2 and experiment 3 data. So then, can you see that the initial rate for experiment 3 is larger than experiment 2? So therefore, we need to use the rate for experiment 3 to divide with the rate of experiment 2. And we are expecting the rate constant for both experiments to be constant. So for experiment 3, so the rate constant is K, but the concentration of CH3COO, CH3 is 0.084. So X, and concentration of hydroxide ion is 0.154 and raised to the power of Y. And this is equal to 3.4 initial rate times 10 to the power of -3. Okay, for experiment 2, the rate constant is assumed to be the same, but the concentration of CH3COO, CH3 is 0.05 raised to the power of X, and the concentration of hydroxide ion is 0.14 raised to the power of Y, and the initial rate is 2.03 times 10 to the power of -3. So K and K, then we can eliminate. 0.154 raised to the power of Y, we can eliminate. And then, since the power are the same, so 0.084 therefore can divide with 0.05 raised to the power of X, which is equal to 3.4 times 10 to the power of -3, divide with 2.03 times 10 to the power of -3, and that should give us 1.86x equal to 1.675. To find x, we can log both sides. So when we log, so the power we can bring to the front. So x log 1.68 is equal to log 1.675, and that should give us x is equal to 0.994. We know that you learn the order, so 0.994, so that is equivalent to first order. So we don't leave our answer x equals to 1. We must write out the order. So the reaction is first order in CH3COOCH3. Then we can move on to find y. So to find y, we need to measure that the concentration of another species, so which is CH3COOCH3, remains constant. So can you see that experiment 1 and 2 having the concentration of CH3COOCH3 remain constant. Therefore, we need to use experiment 1 and 2 data to find y, the order with respect to hydroxide ion. So, and then we can see that the initial rate of experiment 2 is larger than the experiment 1. Therefore, to find y, we need to use the rate of experiment 2 divide with the rate of experiment 1. Okay, so that is 2.03 times 10 to the power of negative 3 divide with 1.58 times 10 to the power of negative 3, which is equal to k. So for experiment 2, the concentration of CH3COOCH3 is equal to 0.05 raised to the power of x, and the concentrations of hydroxide ion is 0.154 raised to the power of y, divide with rate constant k. And for experiment 1, the concentration of CH3COOCH3 is 0.05 raised to the power of x, and concentrations of hydroxide ion is 0.12 raised to the power of y. So k and k we can eliminate. 0.05 raised to the power of x can eliminate with 0.05 raised to the power of x, and that should give us 1.285 equals to 1.283 raised to the power of y. So again, to find y, we can log both sides. When we log, the power we can bring to the front, and that should give us y equals to 1. Again, don't leave our answer as y equals to 1. We must write it is representing which order. Okay, so the reaction therefore is first order. So y is the order with respect to hydroxide ion. So therefore the reaction is first order in hydroxide ion. After we have found what is our x and y, then we need to write the red law. Rate equals to k, concentration of CH3COOCH3 we know that the order is first order, so raised to the power of 1, but 1 usually we don't write it. And then for hydroxide ion, it is also first order, so therefore raised to the power of 1, so usually we do not write it out. So therefore this is the red law or red equation for this reaction. So if the question asks red law or red equation, then we must write our answer in this form. So if the question asks for order with respect to each of the species, we can leave our answer in this form. Now we move on to look at how to determine the order of reaction based on half-life. For this, we need to remember the formula of half-life for zero order, first order, and second order, and also must remember the feature of half-life for zero, first, and second order. So for zero order, the half-life is equal to initial concentration divided with 2K. From the formula of zero order half-life, we can see that the half-life for zero order reaction is directly proportional to its initial concentration. So this means that when the initial concentration is half, then the half-life value will also be half. So this is the feature for zero order reaction. So for half-life, there is only one graph we need to plot, which is concentrations of the reactant versus time. For zero order, so how do we determine the first half-life? So this is initial concentration. So for the first half-life, so must remember half-life is the time taken when the concentration becomes half of its initial value, and the time taken here is the first half-life. For second half-life, how do we determine the value of second half-life? So to determine the value of second half-life, we need to use now the initial concentration, which is half initial concentrations of the first half-life. And for second half-life, so the time taken will be this much. So this is the second half-life. And can you see that? Can you see that? So for the first half-life, this is the initial concentration and this is the half-life value. And for the second half-life, this is the initial concentration, which is half. And can you see that the second half-life, the value is actually half of the second for the second half-life, the value is actually half of the first half-life, because for the second half-life, the initial concentration is actually half of the initial concentration of the first half-life. So this is the feature for zero order reaction. So now we move on to look at first order reaction. So for the first order reaction, the half-life formula is equal to ln 2 over K. So can you see that for the first order reaction, the half-life is independent from initial concentration. Or in other words, the first and the second half-life value will always be the same. Okay, so for half-life, again, there is only one graph we need to plot, which is concentration versus time graph. So for the first order reaction, how do we determine the first half-life? So this is initial concentration. After the first half-life, the initial concentrations will become half of its initial value. And the time taken, we call it as first half-life. For second half-life, we started at half of the initial value. So after second half-life, so the concentrations remain will be half of initial concentrations value. So which is initial concentrations, which is quarter of initial concentration. So this is the second half-life. And can you see that for the first order reaction, the second half-life value is same with the first half-life value. So it's the same. So this is the feature of first order reaction, where the second half-life and the first half-life value will be the same, because for first order reaction, the half-life is independent from the initial concentration. Now we move on to look at the second order reaction. So the half-life of second order reaction is half-life equals to 1 over K initial concentration. So from this, we can see that half-life for the second order reaction is inversely proportional to the initial concentration. Or in other words, when the initial concentration becomes half, then the half-life of the second order will become double, because it is inversely proportional. The half-life of second order reaction is inversely proportional to its initial concentration. So when initial concentrations become half, the half-life for the second order reaction will become double. So again, for half-life, only one graph we need to plot, which is initial concentration, which is concentration of reactant versus time. So this is the initial concentration. So after first half-life, initial concentrations become half. So this is the first half-life. So for second half-life, the initial concentration is half initial concentration. So after second half-life, it will become quarter of initial concentration. And the time taken is what we call as second half-life. And can you see that for second half-life, the initial concentration is half of the initial concentrations of the first half-life, and the time taken, the second half-life, is double of the first half-life, because the initial concentration of the second half-life is half of the initial concentrations of the first half-life. So this is the feature of second order reaction. Now we move on to look at the example on how to use the half-life to determine the order of reaction. So if you have been given concentrations versus time graph, you must know that it implies that you must use half-life method to determine the order of a reaction. So to determine the order of the reaction, you need to first determine the first half-life, and second, you need to determine the second half-life. And then, based on the feature of the first and the second half-life, then we determine the order of the reaction. Like for example, in this question, we are being given initial concentration 0.1. After the first half-life, so the concentrations become 0.05, and the time taken is about 125 seconds. So that is our first half-life, 125 seconds. Then we need to determine the second half-life value. So to determine the second half-life value, so this is the initial concentration for the second half-life. After second half-life, the remaining concentration will be 0.025, and that is equal to it is equal to 380 seconds minus, so here is the second half-life. So which is equal to 380 seconds minus 125 seconds. That is equal to 255 seconds. And can you see that? So the second half-life is about double of first half-life. So this indicates that it is second order reaction. Therefore, the reaction is second order, and our reactant is Hi, so second order in Hi. So this is how we use the half-life method. So remember half-life method, we need to determine first and the second half-life, and then look at the features of the half-life in order to determine which order is the reaction with respect to that particular species. And for the half-life method, it must be concentrations versus time graph. Now we move on to look at how to use the linear graph method to determine the order of a reaction. For this, we must remember the integrated rate equation for 0, first and second order. And I already told you that you remember the integrated rate law for 0, first and second order in linear equations form, y equals to ms plus c. So that easier for you to know which linear graph you need to plot for each of the order. So for 0 order, the integrated rate equation is remaining concentrations of reagent A equals to negative kT plus initial concentrations of reagent A. So this is therefore your y, this is your gradient x, and this is your y-intercept. So for 0 order, therefore the linear graph will be remaining concentrations of reagent A versus time, and it is downward sloping linear graph because the gradient is equal to negative k. So this is the linear graph that you need to plot for 0 order reaction. For first order reaction, the integrated rate equation is ln remaining concentration of your reagent equals to negative Kt plus ln initial concentrations of the reagent. So again, this is linear equation. So your y is ln remaining concentrations of your reagent. Gradient is your negative rate constant. Time is the x. Your y-intercept is ln initial concentrations of the reagent. Therefore, for the first order reaction, the linear graph that you need to plot will be ln remaining concentrations of your reagent versus time. And again, it is downward sloping linear graph because the gradient is equal to negative rate constant. For second order reaction, the integrated rate equation is 1 over remaining concentrations of your reagent equals to Kt plus 1 over initial concentrations of the reagent. For second order reaction, therefore, you know that your y is 1 over remaining concentrations of your reagent. Slope of the graph gradient is equal to the rate constant, and your x is the time, and 1 over initial concentration is your y-intercept. So for second order reaction, the linear graph you need to plot is 1 over remaining concentrations of reagent versus time, and it is upward sloping linear graph because the gradient of the graph is equal to the positive rate constant. So example of the question. So the question asks you to show that change in concentrations of your reagent N2O5 against time, and they give you a table to show the changes in concentrations of the reagent against time, and ask you to determine that the reaction is first order using linear graph method, and find the rate constant K for the reaction. To use the linear graph method to determine the reaction is first order, you must remember the integrated rate equation for the first order reaction, which is equal to ln remaining concentrations of our reagent, which is N2O5, equals to negative Kt plus initial concentration of our reagent N2O5. From the equation, we know that to prove that the reaction is first order, we need to plot ln remaining concentration versus time graph. And if the reaction is first order, we should get a linear graph where we plot ln remaining concentrations versus time graph. And how do we determine the rate constant of the reaction? We can determine it from the gradient of the graph, because from the linear equation for the integrated rate law for first order reaction, we know that the gradient of the graph is equal to negative rate constant. Therefore, to find the rate constant, we first need to determine the gradient of the graph. How do we find the gradient of the graph? We can find from the big triangle. So for the y-axis, it is negative 1.2, and for the x-axis is 4.3. So we get our negative and negative, we can eliminate. Therefore, we get our rate constant equals to 0.2791. And what is the unit for the first order reaction? It should be equal to per time, and the unit for the time here is minute, so therefore the unit will be per minute. So this is how we use the linear graph method. to determine the order of the reaction, and then we use the linear graph to determine the rate constant of a reaction. Now we move on to look at the 1.1h, perform calculations using integrated rate equations. So to perform calculations using integrated rate equation, you must remember the integrated rate equation for zero order, first order, and second order. For zero order is remaining concentration equals to negative kT plus remaining concentration of the reagent. For the first order is long remaining concentrations of reagent equals to negative kT plus long initial concentrations of the reagent. For second order is 1 over remaining concentration of reagent equals to kT plus 1 over initial concentrations of the reagent. To do the calculations using integrated rate equation, sometimes they do not tell you the order of the reaction, but they give you rate constant. So to know the order of a reaction, we can refer to the unit of the rate constant. Must remember, for zero order, the unit of the rate constant is equal to the unit of the reactions rate, which is equal to molar per time. For first order, the unit of rate constant is per time, while for second order, it is per molar per time. So we need to know the order of the reaction first, then only we will know which integrated rate equation we can use to perform the calculation. So example of the question. So this question is very good-hearted because they tell you the order of the reaction. Then straight away you know that you need to use the integrated rate equation for the first order in order to do the calculation. But if they do not give you, then you need to look at the unit of the rate constant to determine the order of the reaction. Then only you decide which integrated rate equation you need to use to perform the calculation. So that is the first thing. We need to determine the order of the reaction, and then from there we choose the integrated rate law equation to be used to perform the calculation. Like for this question, it is first order, so we use ln. So in this question, our reagent is not A, it's N2O5. Therefore, it is important for us to write N2O5 in the equation to replace the A in order to get the mark for the equation, for the formula. So in this question, we are being given the time, asked us to find rate constant K. We are not being given initial concentration. So what we can do is we can assume. So we can assume our initial concentration is equal to 1 molar. And the question says 25% decompose. And in the formula here, this is referring to remaining concentration. 25% decompose means that remaining will be 75%. Initial concentration 1 molar, therefore remaining concentration is 0.75 molar. Then we can substitute into the formula. To find the rate constant. So time is 10 minutes. Initial concentration is 1. So therefore the rate constant is equal to 0.02877 per minute. This is first order reaction. Therefore, the unit of rate constant is per time, so per minute. So 1.2, there are no C3, C4 learning outcomes, so we skip 1.2. We move on to 1.3, factors affecting reactions rate. So 1.3b illustrates the effect of temperature on reactions rate using Maxwell-Boson distributions curve. So this is C3. So possible to come out in PSPM. So to use the Maxwell-Boson distributions curve to illustrate the effect of temperature on reactions rate. So first we must know the axis. So in the Maxwell-Boson distributions curve, the y-axis is the number of reacting molecules in the system, and the x-axis referring to the kinetic energies of the molecules in the system. So at low temperature, only this much of molecules with kinetic energy equal or greater than the activation energy. So, however, at higher temperature, so higher temperature means that now the reacting molecules will have higher kinetic energy. Therefore, the whole graph will shift to the right, move to higher kinetic energy. At higher temperature, so the amount of molecules with kinetic energy equal or greater than the activation energy is this much. So which is greater than the amount of molecules with kinetic energy equal or greater than activation energy at a lower temperature. So what conclusions can we make based on the curve? We can say that at higher temperature, more molecules with kinetic energy equal or greater than the activation energy. Therefore, the number of effective collision and also the frequency of effective collision increase, and therefore the reactions rate increases. So this is how we use the Maxwell-Boson distributions curve to illustrate the effect of temperature on the reactions rate. Now we move on to learning outcome 1.3c. Compare the curve of the energy profile diagram for a reaction with and without catalyst. So first, we must remember the axis. The y-axis is energy and the x-axis is reactions progress. And then we must look at whether the reaction is exothermic or endothermic. Like for this reaction, it is exothermic. Therefore, the product lies at lower energy level than the reactants, and the delta H therefore is negative. And then we must include the activation energy without the catalyst. So without the catalyst, the activation energy is from the reactant to the highest energy level. So this is activation energy without the catalyst. With the presence of catalyst, so first you must understand what is the functions of catalyst. So basically, catalyst provides an alternative pathway with lower activation energy. Therefore, you need to draw a pathway with lower activation energy and then label from the reactant to the top. So this is the activation energy with the presence of catalyst. So basically, catalysts provide an alternative pathway with lower activation energy, which allows more molecules, reacting molecules, to have kinetic energy equal or greater than the new lower activation energy. This causes the number and also the frequency of effective collision to increase and causes the reaction rate to increase. Now we move on to look at the learning outcome 1.3f. Determine rate constant K, activation energy EA, temperature and frequency factor using Arrhenius equations by calculation and graph. So first you need to remember your Arrhenius equation. So Arrhenius equation is K rate constant equals to A frequency factor exponential negative EA over R 1 over T. In Arrhenius equation, the T here is referring to absolute temperature, and therefore in the calculation must make sure that the temperature is in Kelvin. And R here is referred to the universal gas constant, having the value 8.314 unit joule per mole per Kelvin. And since the unit for universal gas constant is in joule per mole per Kelvin, therefore in the calculation we must make sure that the unit of activation energy is in joule per mole as well. Usually activation energy unit is in kilojoule per mole. So to use the EA in calculation, must remember to convert it to joule per mole before we perform the calculation. For Arrhenius equation, we can also remember it in the linear equations form, so that easier for us to plot the graph and to perform the calculation. So this is the Arrhenius equation in the linear equations form, where long K is the y, negative EA over R is the slope of the graph, and 1 over absolute temperature is the x, and ln A is the y-intercept. So for Arrhenius equation, if we are being given 2 temperature and 2 rate constant, it can also be modified into this form, ln K1 over K2 equals to EA over R 1 over second absolute temperature minus first absolute temperature. So when to use the third Arrhenius equation, the modified Arrhenius equations form, it is when we have 2 rate constant and 2 temperature given. So now we move on to look at the example question. So like in this question, we have been given 2 temperature and 2 rate constant and ask us to find the activation energy. So for this, no doubt we need to use the third equation, the modified form of Arrhenius equation, to do the calculation for us to determine activation energy EA. So for this, we know that we need to use the third equation. So we need to write out the formula first to get the mark for the formula. Then we can substitute all the informations that we have into the formula. So our K1 is 1.74 times 10 to the power of negative 5. Our K2 is 6.61 times 10 to the power of negative 5. EA, we want to look for it. R is 8.314 joule per mole per Kelvin. T2 is 35, but remember, it's absolute temperature, so must convert to Kelvin. So T1, 25, convert to Kelvin. Then we can press our calculator to find the EA. So how to press the calculator? So first we need to press ln 1.74 times 10 to the power of negative 5 divided by 6.61 times 10 to the power of negative 5. Divide with this, then multiply with 8.314 in order to get our EA. So EA therefore is equal to 101,951 joule per mole. For activation energy, we need to write the unit in kilojoule per mole. Therefore, we need to divide it by 1000 to give us the activation energy as 101.951 kilojoule per mole. Sometimes the questions could ask you to discuss how to determine the activation energy using graphical method. So how can we determine activation energy using graphical method? So first, you need to remember the Arrhenius equation in the linear equations form. So which is ln K equals to negative EA over R 1 over T plus ln A. So from this linear equations form of Arrhenius equation, we know that the y-axis of the graph must be ln K, negative EA over R is the gradient of the graph, and 1 over absolute temperature is the s-axis of the graph, and ln A is the y-intercept. Then we can say that in order to determine the activation energy graphically, we need to plot ln K versus 1 over T graph, and we are expecting to get a downward sloping linear graph. And how can we determine the activation energy from the graph? We know that we can determine the activation energy from the slope of the graph. The slope of the graph is equals to negative activation energy over universal gas constant. Therefore, to get the activation energy, we just need to bring the negative over, so become negative slope of the graph multiply with universal gas constant. So this is how we discuss how to determine activation energy using graphical method. So again, we start with writing the Arrhenius equation in the linear equation form. Then talk about what graph we need to plot. And then from the graph, remember the gradient of the graph or the slope of the graph is equal to negative EA over R. And to find the activation energy, basically we just need to bring the negative over, become negative slope of the graph, multiply with the universal gas constant.